Hello everyone, how are you? I hope you are all doing well. In today's lecture, we are going to study magnetic and the electric energy density. Okay, so basically, in case of magnetic energy density, first of all, we are going to derive the equation of we can say magnetic energy, and then we are going to derive the equation of magnetic energy density. So for magnetic energy density, we are going to use this example. For this case, we are assuming that we have a solenoid of 1 turns per unit length, and the I current is flowing through it. So the magnetic field due to a solenoid we are going to use, and the properties of that we are going to use. So first of all, let us assume that assuming first of all, let me write assuming a solenoid of and turns per unit length, a solenoid of and turns per unit length if the current I is flowing through it, the magnetic field will be magnetic field due to a solenoid is, as we all know that it is B equals to mu naught times N into I. This will be the magnetic field. Okay. And as we know that the energy stored in a energy stored in a in a we can say solenoid is, since the energy stored in a solenoid is, what is the energy stored in a solenoid? As we know that it is 1 by 2 Li square, where L is where L is the self-inductance of the coil. Self-inductance of the coil. Okay. And now we are going to substitute the value of, or we can say the expression of current I from the magnetic field expression of a solenoid. That is B equals to mu naught Ni. So therefore, the equation of I will be from the equation one. Let me denote it equation number one. Equation one. Okay. So from equation number one, we can write that B equals to mu naught Ni. So therefore, I will be B upon mu naught N. This will be the equation of I. Now the we can say the energy stored there. Therefore, the energy will be UB equals to 1 by 2 L, and in place of I, it will be B upon mu naught N and its square. And we also know that the self-inductance of a coil is given as, since since L equals to mu naught N square, A into L. This is the equation of self-inductance. Okay. So now we will place this in the above equation. Then finally we will get UB equals to 1 by 2 mu naught N square into A into L. and this equation will become b square upon mu naught square into n square. This will be the equation. So from here we can see that n square and n square will be cancelled out, and one we can say from the square of mu naught, and mu naught will be cancelled out, and only one mu naught will be left in the denominator. So finally we will get the equation as ub equals to 1 by 2 1 by 2 and b square upon mu naught into A into L. This will be the equation of magnetic, we can say the energy stored in the solenoid. Now, now from this equation, we are going to derive the equation of energy density. Okay. It is energy stored, or we can say stored energy. This is the equation of stored energy. Now, the energy density we are going to find out. The magnetic energy density. Okay. Or magnetic energy density will be given by the magnetic energy divided by its volume. Okay. So basically it is written as UB equals to capital UB divided by volume, where what is V? V is the volume. Okay. Now, what will be the volume? Volume, we know that the cross-sectional area into length will be called as volume. So therefore, the equation will become as UB equals to capital UB divided by area into its length. Now, we will place the values expression of the, we can say, capital U, and finally we will get the magnetic energy density. So it will be 1 by AL times UB, equation of UB, that is 1 by 2 B square upon mu naught, B square into mu naught into AL. This is the equation. So from this AL to AL, it will be cancelled out, and finally we will get the equation of UB. It is, we can say it is 1 by 2 mu naught B square. This will be the equation of magnetic energy density. Okay. The magnetic energy density. Now our first task is done because it was the magnetic energy density. Now we are going to derive the electrical or we can say electrostatic energy density in case of capacitor. Okay, so in case of capacitor, parallel plate capacitors, let me write the heading first. The electrostatic energy density, and it is denoted by UE. Okay, as we know that in case of parallel plate capacitor, we can say that in case of parallel plate capacitor, where the plate separation is given as of separation D, the electrical energy is given by, okay, the stored energy it is given by UE equals to 1 by 2 CV square, or we can say half CV square. This is the energy stored in a capacitor. Now we are going to derive equation in terms of electric field. Okay. So here we know that, as we know, the capacitance can be written as capacitance is C equals to A epsilon naught by D. Okay, where A is the cross-sectional area, epsilon naught is the permittivity of free space or vacuum, and D is the separation between the parallel plates. Okay, so let me write where A is cross-section area of plate, and epsilon naught is permittivity of vacuum, and D is separation between plates. So, and what is the we can say electric field in terms of electric potential? It will be, and let me write, and the electric field will be, as we know that electric field between the plates of the capacitor is given as E equals to V by the separation D, where V is the electric potential, where V is electric potential. Okay. Now, what will be the electric potential in terms of electric field? It will be, if we derive, then it will be V equals to E times D. So now, therefore, the equation will become as, therefore, the energy, now, the energy expression. What is the energy expression now? It will be, now we have to place the value expressions, sorry, UE. So the equation will become as 1 by 2. In place of C, we have to write A epsilon naught by D. And in place of V, we can write E into D and square. Now the equation will become as 1 by 2, 1 by 2, A epsilon naught D and E square into D square. So from this one, D and D square, one D will be cancelled out, and we will get the equation as UE equals to half epsilon naught, wait, half epsilon naught E square, half epsilon naught E square, and what is left? A into D. A into D. This is the equation. Okay. So from this equation, this is the equation of stored energy, and now we are going to derive the equation of electrostatic energy density. Okay, this is the equation of stored energy. Now we are going to derive the equation for electrostatic energy density. Electrostatic energy density. What is the electrostatic energy density? It is similar as the magnetic field, like the electrostatic energy divided by the volume we will get. So it will be UE will be equals to capital UE upon volume. Similarly, here the volume will also be equal to area into the separation. E equals to UE divided by area into the separation. And finally, we will get the equation as the equation as 1 by A into D and 1 by 2 epsilon naught E square A into D. This was the equation. So finally, we will get the equation of electrostatic energy density as UE equals to half epsilon naught E square. This is the equation of energy density. Okay. Energy density. Hence, we have derived the equations for both magnetic energy density and electrical energy density. So magnetic energy density is given as UB equals to 1 by 2 mu naught B square, and the electrical energy is given as UE equals to 1 by 2 epsilon naught E square. I hope you understood these two derivations. If you have any doubt, then you can ask in the comment section.